Good morning. Today, our topic of discussion is curvature. We are familiar with the different types of curves, plane curves or space curves, and we have straight lines in space and plane. Also, we have circles, parabolas, etc. So, for the case of a circle, if we consider this point, we have a tangent here. And we know that the next, as moving from this point to other points, the curve moves away from its tangent at the previous point. So how quickly a curve bends is a problem for us. And curvature measures such a value. That means how quickly a curve bends. Or if a curve R is a curve of within the parameterization, that means R of S, then we know that its tangent vector is R bar dash of S is same as its unit tangent vector because its speed is u1. So we have this is equal to T of S, the unit tangent vector T of S. And actually curvature of this curve it is also a function of S, and that is defined as the length of the rate of change of the tangent vector. That means we have T unit tangent vector. That means we have T of dt by ds. Length of the or modulus value of the rate of change of the tangent vector. That means we have, if R of S is a curve with after the parameterization, then curvature, it is denoted by the Greek word kappa. Kappa of S is defined as the magnitude of the derivative of the unit tangent vector with respect to S. And we know that here we take the Artin parameterization for obtaining the unit speed tangent vector. We can represent this kappa in terms of t also. For that we know dt by dt. S is a function of t. If R of t is an arbitrary parameterization, we can take the unit Artin parameterization as a function of t. Then dt by dt can be evaluated as dt by ds times ds by dt. And from this we have dt by ds is equal to dt by dt, small dt, divided by ds by dt. And so we can express kappa of S as modulus of dt by dt divided by ds by dt. And this quantity dt by dt is equal to, we can express it as t dash of t, and this quantity ds by dt is actually, we know that r bar dash of t because it is the Artin parameterization, modulus of r bar dash of t. So we can write it as modulus of t dash of t divided by modulus of r bar dash of t. Or we can write kappa as a function of t because this is a function of t. We can write it as the curvature as kappa of t is equal to t bar dash of t by modulus of r dash of t. And using this equation, we can have the curvature of a curve in terms of t. So for that we consider a circle of radius a, and we want to find the curvature of a circle of radius a, and we here assume that the circle is centered at the origin. So we can have a parameterization like this. R of t is equal to a cos t I plus a sin t j, where 0 less than or equal to t less than or equal to 2 pi. And for this we have r bar dash of t is equal to minus a sin t I plus a cos t j, and here we have t is equal to, we know that it is actually the unit tangent vector is defined as the as the unit vector parallel to this direction. So we have r dash of t divided by modulus the length of vector r dash of t. So that is equal to minus a sin t I plus a cos t j divided by modulus of a square sin square t plus a square cos square t, that is equal to modulus of a. And now we have half a of t is equal to modulus of t dash of t divided by modulus of r bar dash of t, and from here we have t dash of t is equal to minus cos ti plus a sin tj minus a sin tj divided by modulus of a. Also modulus of r bar dash of t is equal to, again we have modulus of a. So this is equal to modulus of a square, and modulus value of this is equal to again mod a. So we have the answer is, final answer is 1 by modulus of a, or if it is radius a, we know that is equal to 1 by a. So the curvature of a circle is modulus of 1 by its radius. That means we know that for bigger curves we have smaller curvature, and for small curves we have bigger curvature. Thank you.